Hello, everyone. Thank you for being here. I am Ricard Borrell, as he said. Thank you for the presentation. I work at Polygon. Basically, I work on developing and optimizing ZK technology. And yeah, this presentation is about leveraging high-performance computing for efficient star provers. The presentation is divided in two parts. First, I will talk about the present in terms of product, which is the ZK-EVM. And I will explain a little bit the lessons learned on the development of the ZK-EVM. And then I will talk about the future, which is what we are working now, which is the ZK-VM, so a general purpose proving system based on stars as well. Okay, let's go for the ZK-EVM. The ZK-EVM was released 2 years ago, and its prover is based on a Stark method. And well, we have an Stark, and then we have aggregation so we have a recursion process to aggregate proofs, and then with a certain frequency, we will send the proofs to L1. Okay. The only thing that we need to understand about an Stark for this talk is that it basically has two stages or two phases. In the first phase, we will compute the trace, and then in the second phase, we'll take the Frey polynomial, which is kind of a summary of all the trace in a single polynomial, and we will prove the proximity to a low-degree polynomial. Right? The commit phase is done in different stages. This means that the trace is filled in different stages, and this is because we need randomness for some of the stages. We need some random numbers to evaluate some of the polynomials of the trace. And this randomness is obtained from the previous stages. So the roots of the polynomials evaluated in the previous stages are committed to the transcript or are added to the transcript, and then we get randomness for the next stage that we have to evaluate. Okay, in our arithmetization of the ZK-EVM, we have 1,300 more or less polynomials, and then the number of rows of the trace, which is something that we can fix, it's a parameter of the prover, let's say, it's 2 to the 25. So it's about 32 million. This is quite a lot, and it ends up posing requirements of 800 gigabytes of memory. Okay, I will talk more about this. Okay, so why we use such a big number of rows on our trace? Basically because we have a monolithic approach on the arithmetization. This means that we have a static capacity, so our trace, the capacity of our trace is determined by the number of rows. And so we fix a big number because basically we want to be able to handle any transaction that comes to the network. Okay? That's why for the most heavy loaded transactions, the ones that will need more steps, we need to have enough space to handle them. Okay? This approach has advantages, but also some disadvantages. A clear one is that, okay, when we have to close a batch because we don't have more room for new transactions, because some of the state machines of the trace are filled, then there will be some spare cells on the trace that we have to prove, but they are not being filled with real values coming from the inputs. Okay? So we have some padding effects. But also has some advantages, for instance, that we have like a constant workload that we can optimize very well. We can allocate buffers on advance, etc. So it also has some advantages related to performance. Now, let's talk about timings. A proof of this huge trace for the ZK-EVM takes about 6 minutes. And the cost with the GCP instance that supports AVX 512, it's only $0.46. Normalized by the number of transactions, Ethereum transactions that we can fit within a batch, it's about $0.2 million. This would be the overhead per transaction. Okay, so it's a very low overhead, which is negligible in terms of the grand scheme of things, in terms of the cost that adds to the transaction. Moreover, OKX has done a very interesting job that it has ported the prover to GPUs, and this has decreased the latency to about 3 minutes. Okay, So, and even decreasing the cost. So this is a perfect situation where we decrease the latency at the cost by using GPUs. Those are numbers given by them, and at the end we end up having $0.1 million added on the cost of the transaction. Okay, so it's really good. The speed up obtained from the CPU to the GPU, it's only, if we consider the end-to-end proof from the beginning to the end, it's 2x. Here is one of the limitations of the prover. As we have such a huge trace, at the end we will be transferring a lot of data between the host and the device during the execution of the kernels. Okay, we will be limited by the PCI Express. However, still, if we look at the real cost, at the end what matters, they are very low. So it's not something that is very relevant in the current context. If we go a little bit deeper and look into the kernels distribution when we do a proof, it's a perfect situation or a good situation because we have that 95% of the time of the proof, it's just concentrated in 4 kernels, especially in 2, which are the entity and the Merkleization, which take 70% of the time. And then we have expressions that are linear combination of polynomial, and then the executor, which is the first phase of the trace evaluation. So it's the part of the trace evaluation that depends on the inputs. Okay, this is the initial execution of the inputs. So basically, we have to focus on these 4 kernels, basically on 2, and that's what we did. A lot of work on this on the past, before releasing the ZK-EVM. The first thing you have to consider when you want to optimize the code is to understand where are the boundaries for this code. And basically, you have to do a roofline analysis. Basically, the roofline analysis shows you where is the limit depending on the arithmetic intensity of your kernel. Okay? If your kernel does a lot of operations per each field element that you upload to the cache of the CPU, it means that it will be bounded by the CPU, by the computing part of the process. And if you have a lower arithmetic intensity, you are becoming bounded by the memory transfers from the main memory to the cache of the CPU. In our case, we are basically bounded by the memory transfers for all the kernels except the hash. And this makes sense because the hash does a lot of arithmetic operations per each field element involved in the hashing. Okay? So we focused a lot on optimizing the entity. We did a lot of, basically the focus here was to minimize the L3 misses. We got, well, at the end, the result the performance that we get is to perform the entity on 100 polynomials of size 2 to the 23 to 1.9 seconds. This is more or less the reference. And then the Merkleization, of course, is about, in the CPU is another thing. In the CPU, it's about vectorization. So taking advantage of the vector registers to do, in each clock, to try to do 4, 8 operations at the same time. And we go to a performance with Goldilocks 1, not Goldilocks 2, of 1 million hashes per second. Okay? So this is the summary of what we did more or less 2 years ago before launching the ZK-EVM. At some point, we arrived to the conclusion that keeping improving the prover would not have any relevant impact on the performance of all the ZK-EVM because the prover was not a bottleneck at all. Okay? So we were very happy with the performance that we were delivering to the application. Okay, that's a good situation. We can focus on other stuff, and that's what we are doing now. The project in which we are involved is the CISC ZK-EVM, which is a general purpose ZK-EVM. Basically, as others that are in the space, we want to prove any program that is written in a high-level language like Rust, CPP, or others. Okay? The motivation of doing this project, it's very meaningful for us because we have acquired a lot of experience, a lot of tooling, a lot of knowledge on running the ZK-EVM, which has been in mainnet 2 years and has been, well, we have struggled a lot with performance, etc. So we can take advantage of all these things that we have learned to put them in the service of this new project, which is more general and can be more impactful in general for any user. Okay, it's open. You can check the GitHub. It's not it's not everything complete to do a proof, but it's almost there. So maybe in 1-2 weeks we will be able to prove any code that comes written in Rust. Okay, now, the main difference with this new proving system, so the proving system that we are doing for ZISC, it's different in many ways, but the main difference comes from the arithmetization, because now we don't have anymore a static capacity for the trace. We will have a dynamic capacity. This means that we will shape the trace depending on the inputs, okay? And it will be divided into different 8 instances. All this will be explained in the next talk, so I kind of skip the responsibility of explaining this well, but of course I encourage you to stay to understand all the implications of this, okay? On the proving time, basically you will have to prove all the instances that you have generated on the arithmetization. We call them subproof. So we have an array of subproofs to be proven, and then of course we will have an aggregation phase on which we will aggregate all the proofs resulting for all the instances that will result on a single proof, okay? Let's think about the computational implications of all of this. In fact, on the CPU efficiency, out of the box, you don't get anything of this. You get worse CPU time. Why? Well, basically, the GPU, the cost of one proof is proportional to the area, and this stays true even when you go to small instances, okay? So you have proportional cost. You have divided the main trace into different subtraces, but the area is more or less, the sum of the areas is more or less the same. Of course, we have eliminated the padding effects, that this is helpful, and it will reduce a little bit the overall area, but it's not a big difference. And we have added the aggregation costs. So at the end, we are kind of making the proof a little bit more costly. However, with this new granularity, there are a bunch of opportunities. And the most important one is that we can take advantage of accelerators without having this limitation of being to move data back and forth from the host to the GPU, okay, with this PCI Express limitation. So this is one very important improvement here. We will be able to exploit GPUs much more efficiently. We have other ideas that vectorizing the execution of Starks. So we can kind of run 8 Starks at the same time with trying to do every operation in a vector register containing elements of different Starks, okay? These are some kind of ideas that we are considering, but the most appealing idea for us is going to distributed computing. Basically, the idea of distributed computing is that you want to run your proof using not one single instance on the cloud, but various instances, and with this try to stronger scaling your application. Okay? You want to reduce the latency, which is one of the main focus of this project. Okay, so let's talk about distributed prover. First of all, we are very happy, or we have a very important advantage on this project, is that we have access to a supercomputer, which is called Selenius. It's part of the CC Euro organization in Netherlands. Okay, it's part of the Euro HPC, but the division in Netherlands, let's say. And we were granted of resources there to do our proofs. We kind of submitted a research project where we want to find the limits of proving a Stark. We want to see where can we go, how far can we go on the reduction of the latency. Okay, this is our goal. There it's free lunch for us. We have hundreds of thousands of CPU cores that we can link together in a proof. We won't go to at this level, but hardware is there. And we have hundreds of GPUs as well that we could link to run a proof, okay? Nonetheless, we want to target the high-end performance available, but all that we are doing can be running on the cloud as well. So we want to reproduce at a lower scale, we want to reproduce the results on the cloud. And this is very important because the production won't be done on a supercomputer, it will be done on a cloud system like the ones that we are using today, okay? Let's talk about the first part, filling the trace. The witness computation is the part of filling the trace that comes from the input. How will we do this in a distributed environment? The most naive way to do this would be, okay, I have several processes. I talk about processes and threads here. Two processes don't share memory, so are processes distributed across the network, and then the process spawn threads, okay? So you can assign one process the master role and say, okay, you will compute the trace, and then send distribute the result into equal parts, and then send to the others. Okay? This is a functional approach, but it's not scalable at all. So we are not parallelizing anything. We have a lot of memory requirements in the master process, and we are also adding a high communication overhead. So it's not serious approach. Now, let's try to get rid of the communication costs. Let's do the computation of the witness redundant in every process. Okay, that's fine. We have get rid of the communication costs, but we are not accelerating because it's redundant, and we have high memory requirements in all the processes because all of them have to store all the trace. So not still there. Okay. The next strategy that we have been developing is, okay, let's minimize the trace that we generate. So we have divided the trace generation in like kind of 2 stages. In the first stage, we only generate what we call the minimum trace, which is the information that you require to then, in a second stage, restart the evaluation of the trace at any point. Okay? So in a second stage, we can, in parallel, recompute the trace and divide this computation. Okay? So we have this first stage of computing the minimum trace, which is very fast. And then we can, from the information generated in this process, we can distribute the trace between processes. I mean, each process will have had run this first step of generating the minimum trace has been run by all the processes. Then all of them know which is the actual load that have to be distributed, and then all of them take one part and then compute this part, but only this part. Okay, this will scale much better. Okay, let's look at the results. The test that I am using here and in the next slides, it's a program that executes 10,000 SHA-256 hash operations. The indexation that we are generating is not complete, okay? Because, well, as I said, this project is under development. At the actual moment, at that point, we're generating instances for the main and the binaries and some multiplicity tables. But it's enough to understand the results and the potential of this, okay? Now, if we consider as a reference the emulation time, which is executing the program without generating any trace, anything, even not the minimum trace, okay? The time is 0.6 seconds for this program. This means that we are going about 80 megahertz is our speed, okay? The overhead of generating the traces ranges with one instance, with one compute node. It's about 100%, so we are doubling this time, down to 37% on bin instances, in bin computing nodes. So we are going really down. The scalability is not very good, but because we are already very fast on the execution of the trace after, because we are dividing it into threads on a single node. But at the end, and really this overhead is not so, it's very acceptable, okay? Only 37%. Okay, I will go a little bit fast because I am running out of time. Then let's talk about the distributed, how we manage the distribution of the subproofs. So we have to solve the proof for all these instances that have been generated. Here we have, we just need to, so here we have a synchronization point because all these instances have a common, share the transcript, okay? This means that this object to get the randomness for the next stage is shared between all the instances. And this poses some synchronization between the execution of all these instances. Okay, what we do is a communication stage where we share the routes that we have to put to the transcript, and then we get the same randomness in each of the proofs. Let's see the results. Scalability of this phase, generating the subproofs, it's 100% efficiency, okay? We go from 70 seconds down to 3.3 seconds. Okay, it's a little bit suspicious that we have even superlinearity. So if you see the efficiency, which is the line, it goes over 100% at some points. So this is something that is not, let's say, a little bit suspicious. The problem here is that the distributed prover even runs better in a single node because you can fix better the granularity of the threads that you are using for the subproofs. Then if we compare the base point is the distributed proof itself on one single compute node as a reference, then we get something that is more meaningful. Okay, we are getting a parallel efficiency of 80%. That's good. Let's go for the distribution. The distribution, the recursion. Sorry, the recursion will have some communication requirements when we generate the tree, because the subproofs that we are aggregating can be hosted in different processes. We have to transfer to the process that will generate the aggregation. And if we look at the parallel efficiency, really, it's not so appealing, right? It's 44%. Okay, but here the problem that we have is that when we are going down to the tree, at some point we have less aggregations to do than processes. Okay, so there are some resources that are being not used at all. Okay, so if we just release these processes to do other things, the real parallel efficiency related to the hardware that we are consuming is 88%. So it's again a very acceptable parallel performance. Now, if we look at the complete overall situation for all the proof, including the Witness computation, the subproofs, and the aggregation, the parallel efficiency is 78%. We go from 125 seconds down to 12.2 seconds. The recursion is taking most of the time right now. It's 65% of the proof. So this is where we have to focus to optimize the performance, to even decrease more the latency. And the most important conclusion here is that as we have a good parallel efficiency, right, it's 70%, we can increase the latency by 10x, right? We have increased the latency of the proof by 10x, while the costs have only increased 27%. So this is a very good situation to have, because basically it means that you can really decrease the latency without additional costs. So that's why and this can be reproduced in the cloud, because we are not, we don't rely on a very high performance network, because the transferring of data that we are doing is really minimal. We are transferring proofs, or we're transferring roots, which is minimal information. So I am closing with this. So we can reduce the latency at a very low cost increase. And as future improvements, we will focus on the recursion, on some algorithms like stir and multifry. Of course, here there is not the GPU in. So with the GPU, we can even accelerate more, because our performance, now our architecture can support GPUs very well, because the instances are smaller. We can even reduce more the performance with the GPUs, and also run on the cloud infrastructure is our next step. Okay, sorry for extending a little bit, and I can take any question.
Thank you, Ricard. Yeah, round of applause. So we'll have a few questions. Reminder that great for everyone who submitted. The QR code is always in the presentation, and you can also vote them. So we're gonna start, if it's all right for you, with the first one. Could you give an intuition of how do you generate a minimum trace that can then be used to restart the trace at any point? What's the data structure like?
Yeah, at the end, the minimum trace only is kind of evaluating the columns that you require to then be able to extend the trace. And this basically is 2 columns for the main state machine, which is the ones that load data from the memory. It's kind of the A and B register. So it's only 2 columns. From that, the rest of columns that compose the main trace can be generated from this information at a given checkpoint. Okay? So that's basically it. So it's evaluating just a subset of 2 columns.
Great. So the next one voted, can we say ZK-VM basically trades more aggregation costs with better concurrency architecture?
So basically, yeah, that is one way to see it. Although the aggregation costs now are huge, and we have to pay for this aggregation, of course, to have this granularity that we are interested on. But we want to reduce as much as possible it by improving the algorithms. For instance, Plonky 2 has a very fast aggregation. We can do something similar. We have the stir approach that reduces the number of queries that you have to verify on each aggregation step. So we have a package of things that we can do to improve this part. Also, we have to really think which is the granularity that it's more suited for our hardware. So it's not, maybe you can generate less instances if we can really exploit the hardware well, and then the recursion will have less levels, okay? So a lot of investigation, it's coming on this part because, as you saw, it's the one that it's more relevant at this point, okay?
Great, great, great. The next one is, can CISC run programs written in lower level circuit languages? Will they be faster than Rust? Will the gap ever disappear? The top one.
Well, the purpose of this is not this. The purpose of this is basically generate the inputs with a high-level language, okay? Basically, Rust, C++, or any other language. So this is mainly the design point of this. Of course, you may be able to generate some arithmetization or some, and then use the prover as a component that can be it can be self-contained, and you may be able to use it. But the main purpose is just you generate your code with a high-level language. You don't care about anything. You will get the proof of correctness of the execution of this program from the inputs. The inputs of the proof would be the inputs of the program, the outputs of the program, and the ELF of the compilation of the program with RISC-V or any other architectures that we are also considering, like WASM or LLVM. Or, yeah.
Great, great. And I think we got chance with one more, quick. Just trying to be futuristic. Can you give it insights on what could probably be done in order to improve the ZK-EVM or VM prover in 1 or 2 orders of magnitude?
For me, it's clear that we have to go, the distribution vector is a path or a vector of improvement that we have to take, because if you rely on more specialized and complicated hardware on a single, but relying on a single instance, on a single node, we won't accelerate. But we can take advantage of the most sophisticated node available, the most sophisticated hardware available, and compose it, and take it 2, 3, 4, whatever number can fit with a good parallel efficiency. Because we want to control all the time the costs of the proof. If you have parallel efficiency, it means the cost doesn't grow. So that's the trade-off that we really have to take into account.
Amazing. Please give a big round of applause.